Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue this new series on troubleshooting runnability. Please see the previous clip on how to get started. In this clip, we will take a deep dive into data collection and theory for these statistically rare defects. Let us begin by answering a question. When does the web break? Does it break when the tension is too high? Does it break when the strength is too low? The answer is yes and yes. Specifically, the web breaks whenever the applied tension causes a localized stress that exceeds the web's local strength. Thus, it is a local issue. Yet, it is also a very global issue. By this, I mean that the applied tension belongs to the mechanicals and controls of the web machine, and the strength belongs to the web itself. It is not machine or material. It is machine and material. So now let's move on to some important machine and material details before we put the two together. Local stresses are far from uniform. They will be higher on the tight lanes of the web. They will be higher on the outside of the bend in spans where rollers have out-of-plane misalignment. They will be momentarily high when an out-of-wound roll rotates. They will be higher during momentary tension drive upsets, such as seen during speed changes, and so on. My paper, Combined Stresses, shows how to calculate and rank the individual contributions of the most common factors to a reduction of overall safety factor. Thus, you would know which factor is largest and perhaps most deserving of attention. Similarly, the strength is not at all constant across the width or down the length of the material. Unfortunately, the resulting local strength variations are exceedingly difficult to model or measure. Yet modeling has been done successfully a few times, but it relies on statistical representation of measured local weight variations as one example. So, let's put these two ideas of load variation and strength variation together. The specific example shown below is the most common and most commonly studied web material, newspaper. However, this principle will hold for most web breaks and, indeed, many rare defects of any kind. The top plot is a strength of a 1 meter wide web as a function of machine direction position. There are several ways to get a plot like this, all of them difficult and all subject to assumptions. Nonetheless, it gives us a quite plausible result of an average strength of 10 pli in American units, or 1.7 kilonewtons per meter in metric units. The 1 sigma variation of strength is also quite plausible, about 1 pli. The bottom plot shows the supplied load on the same or similar section of material. This is measured quite easily with responsive load cells. Here, again, we see a plausible 2 pli average, though the variation is considerably higher than most modern winders would see. Recall that my widely published guidelines for tension quality are 10%, and here we have something more like 50%. In any case, the average tension is 20% of the strength, and that again is absolutely ordinary, though a little bit on the high side. Nonetheless, even with this slightly high tension setting and extraordinarily poor tension control, we have zero apparent crossing of the load and strength curves. Indeed, it appears nowhere near crossing. So now the question is, why the heck should the web ever break with such a wide separation of loads and strengths? One possible explanation is that both the load and the strengths are the average across the entire width. Obviously, local loads and local strengths will be occasionally higher and lower respectively. Still, are there other explanations? Yes, there is. There is a very strong statistical factor. It has to do with sample size. If you look at the previous plot in detail, you will notice that we only showed a few meters of web length. There are 10,000 times that much length in a single wound roll of newspaper, and 1,000,000 times that much in 100 rolls. That is the basis the paper industry uses to report runnability figures. As we look at more and more and more material, we will find ever higher peak loads. As we look at more and more and more material, we will find ever weaker sections of the web. This statistical behavior goes by many names, such as extreme value or Gumbel distribution. However, my favorite is the weakest link analogy. It matters not what the average strength of the links in the chain are. All that matters is the strength of the weakest link. As we look at more and more chain, we will find ever more weakest links. The same principle applies to loads as well. Thus, we should be super careful about using any lab test measurements using super tiny bits of material to predict what acres of material will perform like. Frost wrote a whole book on the subject of what you can conclude from tiny samples taken from a wound roll. This should be read by anyone in charge of rejectable specs, lab testing, and customer support. Strength, by any measure, does not imply runnability. Here is an example of a very strong web that had poor runnability, simply because it was variable. I once worked on a Canadian newsprint winder where the web was in the 99th percentile for strength, and the mill manager refused to accept that part of the problem was his. That is, until I showed him that his variability was also in the 99th percentile. Very strong, yes, but very variable. Variability dominated the system. So now we have inadequate sample size issues compounded by variability that is seldom measured that makes prediction, problematic. We will soon add another problem to that list. That is, which measure of strength will you use? There are several to choose from. Another concept we can illustrate by looking at load strength distributions is the idea of proof loading. Here we can run a higher tension on an upstream process, such as a mill rewinder, to cull or edit out or splice at least some of the weaker material so that it doesn't reach the customer, say a printing press, for example. If that process were perfect, a 3 pli rewinder tension setting would completely protect a customer running 2 pli. However, since both processes are far from perfect, it only reduces instead of eliminates downstream breaks. So, in summary, runnability is a system issue where machine and material factors can be very difficult to separate. At best, we might define it as a material property on a perfect machine, or a machine property when running a perfect material, if there were even such things. The point being is that we can improve runnability by both material and machine design. Though individual cases may make one arena more physically powerful and in another arena more politically palatable. Thank you so very much for allowing me to share some troubleshooting techniques for a rare event such as web breaks. Stay tuned for the next clip where we will show how to predict runnability. Please be sure to like and share if you found this interesting or useful. See you next time.